All right, so here we are. It's actually, let me go grab a non-squeaky chair. But this is Saturday afternoon through 4:12. Hopefully, I'll get this up tonight. But this is the honors test 2023-2024, and we're going to start with this problem that is from the makeup. Okay, so I think only one person ended up taking this one. I think I lifted this problem directly from WebAssign. So let's go ahead and see what we got. All right, so let's see what we got. A rocket is launched at an angle of 51 degrees above the horizontal. 51 degrees. With initial, it looks like we've got 3 sig figs in every number. So let's just hold on to that. 3 sig figs. Okay, anyway. So 51 degrees, it's got an initial speed. So it starts off here. I'll call this V0 equals 103 meters per second. Rocket moves along for 3 seconds. So 3 seconds is right when it gets, say, here. So I'll call that T1 equals 3 seconds, because right here, this will be my T0 equals 0, right? With an acceleration of 28 meters per second. Acceleration is a bit of a tricky monster here, right? Because it's like, where do I draw that? I don't want to get confused in here. I'm just going to draw it in a slightly different color. We will be learning how to deal with this soon. 28 meters per second squared. Okay, at this time, its engines fail, and the rocket proceeds to fly as a projectile, move as a projectile. So at this point right here, wherever that point is, okay, there's a V1 right here, which we don't know what it is. I put a question mark there. I'm not even sure if it's going to ask for that. But here's our projectile, right? Let's do a better job with the end of that drawing. Drawing on an iPad is not a perfect experience. Okay, so here's the ground. And clearly it doesn't go below the ground, but we'll leave those lines there. Okay, draw a picture. Here's our picture. Basically, from this point 1 right here until here, it's a normal projectile problem. Okay, from this point 0 to this point 1, from here to here, it is a 1D motion problem. Okay, and how do I know it's a 1D motion problem? Well, we know it's a 1D motion because all the velocities, the acceleration, and the movement, okay, are all aligned, okay, or collinear if you wanted to call that. So once everything's aligned, well, it's just a 1D problem, okay? It's just on a 51 degree angle. We don't care, okay? So the key here is that, what we need to know is we need to know everything we can about this point right here, because that sets up the projectile motion problem, okay? So at that point, I'm going to want to know velocity, and I'm going to want to know position, okay? And I'm going to want to know position. Okay, that's what I'm going to need for that particular spot. Once I have that, then this is no different than any other projectile motion problem. Okay, so I'm going to go ahead and do those things. Well, hold on. Let's go ahead and label what it is we're looking for. Let's see here. The maximum altitude reached by the rocket. Okay, let's see here. The maximum altitude reached by the rocket. So it means we're going to want to know some things right here. I've already got 1, so this will be T2 right here. And we want to know this altitude right here. So I'm going to call that Y2. Noting that I'm going to go ahead and make this point my origin right here. So that's going to be 0, 0. Okay, this is already getting busy, right? All right, so let's see here. Find the total time of flight. So I want to know when it hits the ground, what the time is. So that'll be T3. I'm going to go ahead and put that a question mark right there, because I know that I'm looking for that. Let's see what else. Find its horizontal range. So that means I want to know how far away until it lands. So that's going to be x3 is what? I want to know where it lands. And then I usually want the speed. Yeah, how fast is the rocket going when it hits the ground? So I want to know how fast it's going when it hits the ground, right? It's going to be going into the ground, right? So that would be, you can either say v equals question mark, or you can say the absolute value of the vector. Okay, either one of those is what we're looking for. Okay, so those are the things that we need. All right, so before I even organize this projectile motion problem, Okay, like, before I create my X and Y table, so that's going to go over here, X and Y. Okay, I need to know what's going on right here at this critical point right here. So what I'm looking for is basically the initial conditions for the projectile problem. Okay, and as I said a second ago, this is nice because everything is aligned. Okay, so this is just a 1D motion problem. Okay, so what I need to figure out is I need to figure out what delta R is, and I need to figure out what this final velocity is. Okay, and those things will set up my problem. Okay, so if I go over here and I guess I'll keep those things in mind. We will note that the initial velocity for this is 51 meters per second. We know that the time, we love getting the time, right? The time, I'm going to go ahead and call this 0, 1, just because that's the time between time 0 and time 1 is 3 seconds. Okay, but I could also just call it T1, right? Because T0 is 0. So, and we've got the acceleration. Okay, so the acceleration is 28 meters per second squared. And I need two values here. I want V and I want delta R. Okay, so that's what's going on in this beginning bit of this problem. Okay, so let's go down here and let's go ahead and solve this. So to get the final velocity when I have these three variables is not terribly difficult. So I'll say V, you know what, I'm going to put little r's on these. Okay, because that's all in the R direction. Everything is in the R direction. Well, time's not in the R direction, right? So anyway, so I can say the final velocity in the R direction equals V naught in the R direction plus acceleration in the R direction times time. Okay, and this will be time 0, 1. Okay, so this is not a terribly tough problem. It's just the hard part is knowing that you can do this. Wait, why did I put, dadgummit, I put the wrong initial velocity here. My apologies. So that should be 103. 103 meters per second. Okay, so this is 103 meters per second. I'm going to add the acceleration, which is 28 meters per second squared, and then the time, which is 3 seconds. Okay, so V sub R equals 187 meters per second. Okay, cool. So we got that. Check. Now we need to know the distance. Okay, so the distance. Oh wait, let's identify which formula we're using here for that first. Okay, based on what we have, I've opened up a few more possibilities because I now have the final velocity, so that could open up another, thing to use in order to get the distance. I could probably just do like an average velocity, and that would be a good way to get the distance. But I'm going to pretend like I didn't do that just now in case I decided to go a different direction with this. So, wait, oh no, it looks like I'm going to use it. I'm kind of following my key here. There's a few different ways to do it. But let's just do this. VR squared equals, the easy, yeah, okay. This would be the standard way to do it, right? So if you have time, delta R equals V naught R T 0, 1 plus 1/2 A R T from 0, 1 squared. Okay, let's do it that way. It's not the way I did it on my key, but whatever. Okay, V naught in the R is 103 meters per second times the time, which is 3 seconds, plus 1/2 A in the R, which is 28 meters per second squared, times that time, which is 3 seconds squared. Okay, let me get my calculator out. And apparently on my key, I made a mistake because I've just been wanting to make the initial velocity 51 throughout this whole problem. But anyway, so I will have fixed that by the time I post this key. Okay, so there you go. Okay, so that's what the calculator says. All right. So what's great about both of those things is it tells me position and velocity at this very important point because it's the initial point for the projectile problem. However, they're both on an angle, right? And so I need to know, so this VR, by the way, we're going to start calling that V1, right? Because it's at point 1. So I want to know V1 in the X and V1 in the Y. And from here, I need to know delta X and I need a delta Y, or x1 and x2, right? We're going to call that x1, and we'll call that y1, right? So let's call this x1 and y1, okay? Okay, because I'm calling this particular point right here, this is point 1. Okay, so as long as that's point 1, that's where everything begins. Okay, so I'm basically going to try to figure out what this distance is and what this distance is, x and y. So that's going to be x1, this will be y1, and I'm going to try to get my initial velocity, and so this will be vx1, and then there'll be a vy1, like that, right? So I'm just basically, putting these things on a triangle. Okay, so over here, so vx1, that's going to be 187 meters per second. We can use a cosine here because the angle is with the horizontal, 51 degrees, and then we got 187 meters per second sine of 51 degrees. And again, we can use sine and cosine like this because that is the angle with respect to the horizontal, okay? And since this is all 1D, everything is in the same direction, so we can just kind of, almost do this formulaically, right? We don't even, it's almost a thoughtless process. Okay, so equals, 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 equals. I'll just pause it and enter those values. Okay, so that's just plugging some numbers into a calculator. All right, cool. So now we have a projectile motion problem, and these are the initial conditions for the projectile motion. Okay, normally x and y are 0, 0, right? And normally vx and vy are just gotten from trig on a velocity, which is what we've just done. Okay, so I'm going to take those values, and we're going to go up here. We're going to create a little xy chart. I actually think I'm gonna zoom in and put it right here. No, because then it'll be small. That's okay. Okay, we're gonna zoom way in here like this. Okay, so here's x, here's y. Okay, we know for the rest of this. All right, so we know for the rest of this, ax is 0, ay is negative 9.81 meters per second squared. Okay, note this only has to do with the projectile motion portion of this, right? For the burn phase, before it's before it's kind of taken off or anything. I mean, before it's run out of fuel, that is not the case, right? It was accelerating on an angle. All right, so at this point, so at t1, I'm going to go ahead and define t1 as being 3 seconds. Okay, so that means t0 is at 0. So something to kind of be aware of. Okay, so this is basically saying that all time goes back to 0. All time goes back to when the flight started, or when rocket ignited or whatever. When rocket ignited. Okay, there's a lot of different decisions you can make here. I think a lot of you would probably choose to make this 0 seconds and just remembering that you have to add the 3 seconds the whole time. It's kind of up to you. Okay, I'm going to take care of that by using prefixes. You'll see as we get into the problem. Okay, so we know from everything that we just did, what do we call this? V1x and V1y. Okay, so we just solved for all these values using trig. So this is going to be 273.75 meters. Y1 is going to be 338.06 meters. Vx1 is 117.68 meters per second, and one y, excuse me, is 145.33 meters per second. Okay, cool. Okay, now the next point that we care about anything is right up here at T2. Okay, the nice thing here is what do we want to know at that point? We want to know this Y2, right? So if we want to know Y2, then that's all we want right up there. Okay, so we're going to go down here. So this is going to be the time at 2 is unknown. Okay, X2 is unknown. Y2 is what we're looking for at that point. V2 in the X and V2 in the Y. Okay, V2 in the Y is 0 because it is no longer going up, so that's cool. And V2 in the X is the value that just keeps on giving, right? Because the acceleration in the X is 0, so, we have that value, okay? Maybe we can go solve that one right now. I don't know. We can. So let's do it, right? So you should, if you're following along, you should probably copy this thing down somewhere. Maybe I can squeeze it in over here since this is all so small. Okay, so we want to know, let's go get the height, right? Let's see here. What is the maximum altitude reached by the rocket? Okay, let's do it right here. Okay, going up here and looking at what I have. Okay, the key piece of information I have for that particular problem is right here. Okay, so we're definitely going to use that. Now, we will note that we do not have time. So when we do not have time, our inclination is to use the v squared equation. So if we use these values given here, so this is my initial, this is my final, okay, then we will use the v squared equation. Okay, so let's go down here. We're going to use the v squared equation. Maybe we can just keep this kind of in sight. Let's do it over here. No, we'll do it down here. Okay, so v squared, v final, 2 in the y, equals v initial squared plus 2ay, delta y. Okay, now I want to note that because this is a 2 and that's a 1, this is the difference in the height from 1 to 2. Okay, so whatever height we get, we need to add the initial height in order to figure out how high it is total. Okay, so we are solving for this particular guy right here. So when we rearrange this, we'll get delta y 1, 2 equals v2y squared minus v1y squared divided by 2ay. Okay, so if I go in here, delta y 1, 2, v2y, so that's where it stopped, right? Minus v1y, what was v1y? 145.33 meters per second. Okay, we'll go ahead and square that, and we'll go ahead and divide by 9.81 meters per second squared. Okay, so delta y 1, 2 then is, unless I made a calculator error, which is always possible, to 5 sig figs, it's this, okay? Now, if we remember that y1 was some value, what was y1? 338.06, 338.06. 338.06 meters. Okay, so then if we were at 336 and then we went up that much, our final y2, the maximum height, is we're just going to add those two up, and I'll get 14.6 meters, or to 3 sig figs, 1410. 14, well, therein lies the question, right? This should have 3 sig figs, right? Which means 338. So we actually gain a sig fig here, right? 1414, because its least precision is that. Oh, no, wait, because this has 3 sig figs, right? Okay, 1410, excuse me. I keep looking for that magical moment when you actually start gaining digits. Okay, so that's our max height. Okay, 1410. Cool. All right, so let's scroll back out and look at this problem. Okay, what is the maximum altitude released by the rocket? 1410 meters, okay, 2 sig figs. All right, total time of flight. All right, so let's go over here. We are now in this position over here. We want to know how long, T3, we want to know how long does it take to get there. Okay, and again, we can define our time in lots of different ways. So let's go ahead and let's draw another line here. Here's T3. Okay, we want to know what that is. Okay, now what else do we know at that point when it hits the ground? Okay, so I don't know x3. That's what I'm looking for. I think I'm looking for that, right? Am I not looking? I think, yeah, it says we're looking for the range at some point. I know y3 is 0. Okay, so it's going to be 338.06 meters below where it starts for the projectile. Okay, v3 in the x, here's the gift that keeps on giving. Cool. And v3 in the y is unknown, but we are going to look for that, I think, because ultimately we want to know the velocity when it hits the ground. Okay, so we call that v3. Okay, cool. So now we've got all this stuff. Okay, so one of the things that I like to note, Okay, usually in this case, this is no exception, so we want the total time of the flight. When we want the time, come on, zoom in, buddy. When we want a time at a position below where something started, and there was an initial velocity in the y direction, we're going to end up with a quadratic, right? So if we try to use the delta y equation. So that's totally fine. We can do that. However, we note that in this case, we want v3 in the y. So if we wanted to avoid the quadratic, usually you solve for this first, and then you use that to get the time. And so since we want this anyway, I'm going to do it that way. So I'm going to solve for v3 in the y first, and then I'll use that to get the time. Okay, so let's go ahead and get v3 in the y. We're going to kind of try to stay close here. Let's go right here. So to get v3 in the y, okay, again, I don't have time yet. So if you don't have time yet, use v3 in the y squared equals v, and we're going to take this all the way back to position 1, okay, because we know the information at position 1, right? That's what we spent the whole part of the early part of this problem working on, plus 2a delta y. Okay, so this is going to be ay, and the delta y is going to be from 1 to 3. Okay, so okay, again, we're solving for v3 in the y, so v3 in the y equals the square root of v1y squared plus 2ay delta y 1, 3. We're going to put a negative sign on there because we know it's going down. We're not going to worry about the positive root here. Okay, so v3y equals negative square root. Let's see, v1y. Where's the v1y? Okay, right here, 145.33. 145.33 meters per second plus 2 times negative 9.81 meters per second squared. And then we need that delta y from 1 to 3. What's the delta y from 1 to 3? Well, we started at 338 and we went down to 0, so it's a negative 338.06. Negative 338.06 meters. Okay, so v3 in the y equals negative 166.59 meters per second. Okay, cool. So that's going to help us a lot because it's something that we need for later in the problem anyway. However, you know, at the moment we're looking for time. So again, you know, this is a method. You know, you look for the v in the y so you can avoid doing the quadratic equation. Okay, so now that we have that, we can avoiding the quadratic equation. We can say v 3 in the y equals v initial in the y. So in this case, 1y, right? Because we're only doing the ballistic portion. I mean, excuse me, the projectile portion plus ay times t. Now this is the time from 1 to 3, so it's not including that initial 3 seconds. Okay, so v3y equal, wait, let's rearrange this. Sorry. So t13, sorry, it's really funny to me how much I turn into a little goofball when I'm creating these videos. Anyway, so t13 equals, the final velocity is negative 166.59 meters per second minus the initial velocity in the y, v1y, what was that? Okay, that's this number at 145.33. Okay, meters per second, and then we're going to divide by that negative 9.81 meters per second. So this is a wonderful problem. It pretty much tests almost the entire first quarter. And actually, on thinking about it, I realized that there were actually 2 of you that took this test for different reasons, but you know, that's okay. Okay, so that's how many seconds to go from 1 to 3. So if we wanted to know how long it had been in the air at 3, we would basically say, okay, well, that's cool. We want T3 though, right? So we have to add 3 seconds to that. So it's going to be 34.797 seconds. And if we wanted to do this with sig figs, it would be 34.8 seconds. Okay, not so ugly of a number. Okay, so let's see, I think at that, whoa, we got really small there. Total time of flight when it hit the ground. So T3 is 34.8 seconds, right? So 31.8 seconds of projectile and 3 seconds of, you know, burn phase. Okay, so let's see, what was C? Find its horizontal range. So we want to know where it is when all that happens. Okay, so let's zoom in here. Okay, so we're looking for this guy right here. Hey, luckily that, remember, once you have time, the horizontal range is a lot easier. And we're going to do this all in one fell swoop. Okay, so let's go over here to the, I don't know why we have to do it down here, but let's just do it right here. Okay, once you have time, there's a few ways you can do this. You can do it like this, delta x equals v naught t. Well, in this case, it would be v1 t, right? Because we're talking about the initial for the projectile phase, plus 1/2 a x t squared, right? And this would be the time while it was in the air, the projectile phase. So that'd be 1, 3, 1, 3. We're not worried about the initial 3 seconds, right? So this goes away, 0. So I could write this as delta x equals v1 x t1 3, which I think is probably the way most of you guys would do it. The other way you could do it, and it's the same, of course, is we could have said that this is x3 minus x1, or excuse me, like if we follow your equation sheet, right? It doesn't say that. It says x3 equals x1 plus v1 xt 1, 3, and then it doesn't have an acceleration term, right? So I can either solve this and then add the initial, x1, or I can solve this and that will just kick it out for me. So we're going to do this one. So x3 equals, let's see, at the beginning of the projectile phase, x1 was 273.75 meters. Let's confirm. Let's go up here and let's confirm that. Yeah, 273.75, right? And the speed through that entire phase of the projectile is 117.68. So where are we? Where are we, buddy? Here we go. So plus 117.68 meters per second. That's the velocity through the whole time, so it's also that initial. And then the time while it's in the air is, or while it's in the projectile phase, is 31.797 seconds, okay? So this is how far it travels during the projectile phase. This is where it starts the projectile phase. Okay, so all told, that will tell me where x3 is relative to wherever it started. Okay, so we add all that up, I'll get 4,015.6 meters. A most annoying number because the sig figs are obnoxious. So we could write this as x3 equals 4,020 meters. Or like with a number like this, I prefer to just go 4.02 kilometers. That just kind of makes me happier. It's kind of whatever works for you. Okay, and then part D, how fast is the rocket going when it hits the ground? Okay, so in order to get that, basically, you need V in the X when it hits the ground. So that'd be Vx3. And then we need Vy3. We know it's going down, right? We don't even need to look that up, right? And so this would be V3. Okay, so this is just a triangle problem. So in this case, V3 equals square root of Vx3 squared plus Vy3 squared. Okay, so V3 equals the square root of Vx3. What is x3? I think it's 117.68 meters per second. We've been using that a lot. And then Vy3. What is Vy3? Go find that sucker. Where are you at, Vy3, you punk? Oh, there it is, Vy3 right there, 166.59. Okay, cool. 166.59 meters per second squared. Okay, so V3 equals, so we get 203.96 meters per second, or V3 equals 204 meters per second. So that's how fast it's going when it hits the ground. Okay, cool. All right, that's the first one. Now I'll have to go find the second one. So that's a doozy, right? That is a doozy. That's a lovely problem. Okay, I love me some rocket, right? Some rocket problem. Awesome, right? Love it. Okay, let's try, what was this one? I forgot. Oh, yeah, I made this one up. so I like that. I mean, you got it from WebAssign. So this is the key. Most of you got this one. Okay, so this is basically slots 3 and 4. I don't know why I write the word period. I should write the word slot. Okay, anyway, a boy throws a basketball on a 30. I think I said we would assume that this one had 3 sig figs and this half had 3 sig figs. Anyway, so a boy throws a basketball on a 36 degrees sloped roof. Okay, and let's see. So what I'm going to do here is I'm going to draw this, okay, the way that I imagined it. I guess we don't really have anything to do with the overhang here. We don't want to do that, right? So it's going to land about right here. Okay, and that's, we're going to say that is 0.5 meters from the edge. And at its initial velocity going this way is 1 meter per second. 1 meter per second. All right, so the slope on this sucker, I don't really know how to get that in there, right? This is 36 degrees. I had to, correct that because I wasn't so clear. It lands a 0.5 meter from the edge and has a velocity of 1 meter per second of the slope. It will accelerate down the slope at this rate. Okay, so I'm going to draw the acceleration in a different color so we don't confuse anything. So acceleration equals 5.7662 meters per second squared. I want you to note that this number right here, this is, and we will learn this soon, that would be the acceleration if this wasn't a ball, if it was a frictionless block sliding up and down this particular roof. The edge of the roof, where is the edge of the roof, is 3.10 meters above the ground. Okay, so here we go. So let's go from here down to here. That's 3.10 meters from the ground. Okay, so hopefully you can see what this ball is going to do is it's going to go up here. It's going to slow down to a stop, and then it's going to turn around. And then right here, right, we need to know this velocity right here. Right, so this is point 0 right here. This is going to be V1. Right, and that is going to be the projectile. Right, that's going to be, we know its location, we know its position right there. And if we have V1, then it's a projectile motion problem until it hits the ground. Right, so that is essentially what we're dealing with here, right? So we will want to know this. I'm sure this problem is going to ask what this distance is. This is what these problems always do. I say that, I made the problem up, right? So, all right, so one thing to note, I think just to make my life easier, I made X backwards because I drew the picture this way. Okay, some of you guys will also do that. It just means that, to the left is positive X. It just makes my life easier. All right, so just like the last problem, I want you to note that from 0 right here to 1 right here, acceleration, velocities, displacements, they're all in the positive, they're all in the same direction, okay? This R direction, right? This direction right here. I'm going to call that positive R. Okay, if I do that, then what do I know? Well, the initial position, R0, is, is 0.5 meters, right? R final. You know what? Let's not do that. Okay, I know the delta R from the beginning to the end is it's going to end up starting here, and it's going to end up back here, and it's going to go in negative 0.5 meters, right? Okay, I know its initial velocity in the R direction, okay, is upwards at 1 meter per second. Its final velocity, okay, V1 is in the R direction, but I don't know what that is. Right, what else do we have here? Oh, and we know the acceleration is negative 5.7662 meters per second because it is in the negative R direction. Okay, so the only thing we need, I guess, is a little bit easier than the other one because we know where the whole problem is going to begin. At least it's easier in that sense, right? So we know the problem is going to begin right here, and we can call that point whatever it is we want to call it, but we just know that that's where the whole problem is going to be. So we don't need to figure out a position. We just need to figure out this velocity at the end of when it's on the roof. All right, so to get that, we don't have time. All right, so if we don't have time and we want to get the, from these variables, then we're going to use the v squared equation. I shouldn't even say almost every time, okay? There's probably times when that's not the case, but I can't think of it. Okay, all of these velocities and the acceleration are all in that r direction. Acceleration in the r, t, sorry. I shouldn't have been talking while I was doing this, right? 2a in the r, delta r. Okay, so the delta r is that distance along the roof, right? So v1 in the r equals, in this case, it's going to be the negative value because it's going to be rolling down the roof. So that's down and to the left, okay, as I've defined r as being up and to the right. So v naught in the r is going to be 1 meter per second. Okay, that was the initial velocity up the roof, plus 2 times the acceleration down the roof. So it's got a negative sign because it's down the roof, 662 meters per second squared. And the delta r is, it's going to end up down the roof by 0.5 meter. Okay, v1 in the r equals negative 2.6012 meters per second. Sweet. Okay, that will set up our projectile motion problem. Okay, now we know for our projectile problem, we know this value. We know the angle at which it's acting, right? So let's go ahead and get the x and the y for that. Okay, so let's go ahead and get the x direction velocity. So v1r in the x and v1r in the y. Okay. In fact, I'm going to get rid of this r here because now we're going to go in the x and the y, right? So let's get rid of those r's. Okay, so v1 in the x and v1 in the y. Okay, so we're going to do 2.6012 cosine of that angle and 2.6012 sine of that angle. Okay, and I can just, without even thinking, I can do the cosine and the sine because these are the angles with respect to the horizontal. Okay, so cosine goes with x, sine goes with the y, as long as the angle is with the horizontal. Okay, so if I follow my trusty dusty key here, v1 in the x is 2.1044 meters per second. And I'm going to leave a positive sign on that because I decided that x was positive going to the left. And then for y, I'm going to do negative 1.5289 meters per second. Okay, so that will set the stage for my projectile motion problem. For my projectile motion problem, right? Okay, cool. So we are all set up for the projectile motion problem. Let's go see what this problem is asking, right? I already knew this was a projectile motion problem, so I guess I should have read what we wanted. Okay, how long is the ball on the roof? Oh, that's before the projectile motion problem. Okay, so we're back over here. We want to know time. T equals what? Okay, how do we get time? A few different ways to get time. Easiest way, if you have this velocity and if you trust it, is to do, because we don't want to do that quadratic equation, so we're going to do v1r equals v naught in the r plus a in the r times t. So this will be t from 0 to 1. Okay, so that's basically while it's on the roof. Okay, so t from 0 to 1 equals v1r minus v naught r divided by a in the r. So t01, let's see, v1 in the r is negative 2.6012 meters per second minus the initial in the r. What was the initial in the r? Oh, it's 1 meter per second. 1 meter per second. Right. Okay, divided by a in the r, which is negative 5.7662 meters per second squared. So it's the T01. Let's see if we do that particular math. We get about 3.0. Okay, that's good. So we get 0.62454 seconds. Okay, and for reporting purposes, we only want 3 sig figs, so T01, 0.625 seconds. Okay, so that is how long this sucker was on the roof. Okay, 0.625 seconds. Okay, find the ball's total time of flight from the roof to the ground. Okay, find the position of the ball's landing spot relative to the bottom of the shed, and how fast is the ball going when it hits the ground. Okay, so all those are, we're now on the projectile motion thing. So I'm going to zoom in right here, and I'm going to create my projectile. Let's go down here and do it. Okay, so we've got x and y. Okay, and I've got t. We don't want to start at t0, do we? We want to start at t1. Okay, and I think I'm going to, for this problem, I'm going to say T1 equals 0 because nothing is being measured back to the, to the, how long after it hit the roof until it hit the ground. So I'm going to say T1 is the time, at the beginning of the projectile problem. Okay, so actually, and I'm going to give myself a little space, right? Because AX equals 0, AY equals negative 9.81 meters per second squared. Boom. Okay, now T1 equals 0. And then I know I'm going to call my initial position on the top of this roof right here. I'm going to call that 0 in the X. So this is, I'm going to call this 0, 0 down here, right? So that point at the top of the shed, X1 is 0, Y1 is 3.10 meters. This way I won't have any negative numbers. Okay, and V1 in the X and V1 in the Y, right? So I'm going to pull those numbers off of my calculations earlier. So this is going to be 2.1044 meters per second, and this one will be negative 1.5289 meters per second. Okay, so okay, and we want to know a few things, right? So that's the setup for the problem right there. Okay, now T2 is when it hits the ground. Does it ask for that? Find the ball's total flight from the ground. Yes, it does ask for that. So we do want the time of flight. The X position when it hits the ground, we want that. It asks for that. That's part D. The Y when it hits the ground is 0, so that's cool. That's what's setting up this problem. And then the V2X and the V2Y. Okay, the V2X, well, the gift that keeps on giving, 1044 meters per second. And the V2Y is unknown right here. Now the question is, are we solving for it? Let's see. Oh, we do ask how fast it's going when it hit the ground, so we need to get that so that we can get V2 equals what? Okay, so what's going to make our lives a lot easier? As always, our lives going to be a lot easier if we get time. Okay, if we want to avoid the quadratic, which many of you will want to avoid a quadratic because you don't. Actually, I just found out the TI-36 will solve quadratics. I don't know how to do it. I recommend doing a little Google internet search if you bought the TI-36. If you have a 30, well, then you're out of luck. Okay, but anyway, find the ball's total time of flight from the roof to the ground. All right, let's see here. So we need to figure out that time. So as always, if we want this and we want time, okay, get this first, okay, because then we won't have to even worry about a quadratic. Okay, so V2Y. Let's start by getting V2Y. So if I don't have time, which I don't because I don't have it yet, right? Then the answer to this, to get V2Y, is always this. So we'll do V2Y is always to do the squared formula. V1Y, remember 1 is right when it leaves the roof, plus 2A delta Y. Rocky Pup is getting... Hey! Okay, he's going to run off and bark at them in the yard. All right, so here we go. So V2Y squared, V2Y equals... Again, we know it's going to be going into the ground, so I'm not going to worry about the positive root here. V1Y squared plus 2AY delta Y from 1 to 2. So V2Y equals negative square root. That's V1Y. So when it left the roof, V1 and the Y, it was going negative. Wait, we have it right here. It's doing this. Negative 1.5289 meters per second squared plus 2 times negative 9.81 meters per second squared. And the delta Y, well, let's see, it started at 3.10, ended at 0, so it went down 3.10, negative 3.10 meters. Okay, so if we solve this, V2Y, okay, notice that negative sign doesn't matter right there, right? But if we plug all this in, V2Y is negative 7.9473 meters per second. Okay, I don't need that number yet. for anything, so I'm not going to bother, rounding it. Let's go see, where is that going to be useful to us? Find the position of the ball's landing spot. No, don't care. How fast is the ball going when it hits the ground? Okay, so V2Y equals negative 7.9473 meters per second. So I'm going to hold on to that until we get there, right? You wouldn't normally do this, but I'm having to zoom in and out, so you might as well hold on to that. Okay, now what? Okay, so the whole reason we got this was because we wanted time, right? So to get time, if you have velocity, so we've got an initial velocity, a final velocity, and an acceleration, then what we're going to do is we're going to say, well, V2y equals V1y plus AY times t. Okay, and that time is from 1 to 2. Okay, so V2y is negative 7.9473 meters per second equals V1y, which is negative 1.5289 meters per second, plus the AY, well, we know that, it's negative 9.81 meters per second squared, and time. Oh, I didn't solve for time first. Okay, well, this is a little sloppy, but you can do the algebra here. Be careful when subtracting negatives that you remember how to do it. And we get 0.65427 seconds. Okay, and for reporting purposes, that's 0.654 seconds. So where was that? Where's the time? Oh, find the ball's total time of flight. T from 1 to 2 is 0.654 seconds. Okay. Find the position of the ball's landing spot relative to the bottom of the shed. So now we're looking for x2. And remember, x is always easy once you get time, right? So delta x equals v naught x, or no, in this case, it'll be the initial velocity. But the initial velocity is velocity at 1 times time from 1 to 2 plus 1/2 ax t 1 to 2 squared. This goes away because ax is 0. So we're not worried about that. And I can use delta x or x2 interchangeably because the initial position is at x equals 1. So I'm just going to call this x2 because I could say minus x1, but remember x1 is 0, right? So that's always nice. Okay, equals v1 in the x. What's v1 in the x? 2.1044 meters per second times that time, which is 0.65427 seconds. So x2 equals whatever that is. So it lands 1.3768 meters away from the bottom of the shed, which seems totally reasonable. It's not really going all that fast. So 1.38 meters. Boom. Got him. Okay, cool. All right, so now we want to know how fast is the ball going when it's the ground. So we know this. So we need to know V2x. So we can make a triangle. Okay, so we got the V1x, we got the V2x and the V2y. The V2x, which we've used here and there, is 2.1044 meters per second. So there's our triangle. Let's see. So remember, our x is positive this way as defined. So 2.1044 meters per second. Here's our y, tip to tail, 7.9473 meters per second. Here's our hypotenuse. Okay, and that's our v, right? So v equals the square root of the x part of this squared plus the y portion of this, 7.9473 meters per second squared. So v equals 8.2212 meters per second, or v equals 8.22 meters per second. Okay, and we did not ask for the angle, but we could have gotten that by doing the inverse tan of this over that. Okay, note that this has to be positive because it asked for how fast. We wanted a speed. We did not want a direction. Okay, you could have also written this like this. This would have been another way to write the symbol for speed. Okay, so it's 49 minutes. It's Saturday. I got to go walk my dog because he's going nuts. So I hope you guys are having a wonderful day. Take care of yourself. Remember that there's a lot more important things than physics and finals. And what I mean by that is you are important. So take care of yourself. Okay. So you are important, and take care. Okay. And by you, I mean more than just your grade. Okay. So your grades are important too, but they're not as important as you are. So take care of yourselves. All right. Bye.